Hello guys and welcome back to Engineering Hack, where we try to solve engineering problems in a way that's hopefully easy to understand. Today we're looking at the second question of the 2021 midterm for heat and mass transfer. It's a straightforward question regarding a pipe, so a cylindrical shape um, object with a difference in temperature from the inside to the outside, and we're just trying to find out what is the heat transfer in the temperature in the interfaces. The question statement reads like so. A steel pipeline having its inside diameter of 50 mils and outside diameter of 60 mils, carries water with a mean temperature of 80 degrees Celsius. The pipeline is legged with asbestos. The outside diameter of the lagging is 90 mils. The heat transfer coefficient from water to the inside surface of the tube is 1581, and the heat transfer coefficient at the outer surface to the surrounding steel air is 5.82. The thermal conductivity of steel is 46 and that of asbestos is 0.11. Neglect the radiation heat loss from the outer surface of the lagging. 1. Determine the loss of heat per unit length of the pipeline if the temperature of the steel air surrounding the pipeline is 20 degrees Celsius. 2. Determine the outside surface temperature of the lagging. 3. Determine the inside and outside pipeline surface temperature. So first things first, we are ignoring radiation on the outside lighting because if we know this guy's going to be at a certain temperature, it will be emitting radiation. And if there's a difference in temperature between T infinity and T surface, we would have both convection and radiation taking place together. We don't have to worry about that, so radiation is out of the picture. We're only accounting for convection. So that simplifies the problem somewhat. What else? We're given the two heat transfer coefficients. That's nice. We're asked to find, on part one, what is the heat loss per unit length. We're looking for Q dot, right? Rate of heat, and per unit length, so per meter or per L. L being the length of this pipe. Um, we know the temperature of the outside is 20, so that tells me that temperature T infinity here. T infinity is 20 Celsius, and the inside that's carrying the hot water is 80 degrees Celsius. So this is what we have. So therefore we know from the get-go that my heat is going to be flowing from inside out. Now I have the hot water in here, and then afterwards I have my steel pipe. This is my steel pipe, and then I have the asbestos, the lagging with asbestos right here. I'm going to have, therefore, three radiuses, or three radii, I should say, which are going to be defining this problem. And I'm going to go ahead and call them R1, R2, and R3. We could have used the diameters too, but for the sake of being consistent with how we usually do things, I'm going to use the radiuses. And so the three radii that we have are going to be 25, 30, and 45, right? So just half of the diameters given. So this guy here is 25 mils. This guy here is 30 mils. And this last guy here is 45 mils. All right. Now, what else? Well, we're going to have different resistances here, right? Because the convection coefficient are given, so therefore we are going to be accounting for the thermal resistance when a solid finds a fluid or when two different fluids find each other, so in the interface, right? So we're going to have to account for that. So that means we're going to have a thermal resistance between the air and the asbestos and between the inside water and the steel pipe. Now, the second part of the problem is asking us to determine the outside surface temperature of the lagging. And that is right here, right? So the outside, so this guy here. And I'm going to go ahead and call this T1, I guess. So T1 over here, and then number 3 is asking us for the inside and the outside surface temperatures of the pipe. We know that this guy here that I just put in red is a pipe, so therefore they want the inside and the outside. This would be the outside, this would be the inside. So the problem is asking, for this guy I'm going to call this T2, and this guy I'm going to call T3, right? So just to be consistent, we're going from outside inwards, and that's going to be from T1 to T3. All right. If I were to draw a equivalent circuit, electric circuit, I would have on one end the 20 Celsius from my T infinity, and then the resistance between air and asbestos, a resistance due to the asbestos itself, a resistance due to the steel pipe, and then a resistance between the water and the steel pipe, right? So these would be my four resistances. Right here, this is where I would have my T1. Right here, this is where I would have my T2, and here is where I would have my T3. This resistance here is due to convection between air and asbestos. This is due to conduction for the asbestos. This is due to conduction for the asbestos as well. And here, this is due to convection between the water and the steel pipe. So what is our game plan here? Let's just put down the things we're looking for. So this we're looking for T1 here. I don't need this guy. There you go. So T1 here, this is what we're looking for in each of these parts here. On part 3, I'm looking for T2 and for T3. Okay, so I'm pretty much solving the whole problem. First thing to note is that as my heat is going from the inside out, there's no other way for it to find T infinity unless it goes through all the layers, right? So there's no way it can get around, for instance, the asbestos to reach the outside without going through all the layers. So that means that this is a system that is in series, so that this is how it looks like if it were an equivalent um, electric circuit, which means that I can convert this into a single resistance, a equivalent resistance if I just sum up all the resistances that we have on this problem. Okay, so game plan is let's find each of these resistances one at a time. We sum them all up, we get this guy here, equivalent. With that, we find what is the Q, what's the energy that's flowing through these guys, because it's going to be the same energy flowing through all of these, right? It's from right to left in this drawing that I put here. And once we get to that point, then we can find Q over L, and then we can find the different temperatures we're looking for. So in order to solve part 1, what we're going to do is first find the resistances. Let me just give them some names so that I'm going to do RA, RB, RC, and RD. Okay, so let's start with RA. That's going to be resistance due to convection, so that's just my the coefficient on the outside and the outside area, surface area. So that's just going to be 1 over the outside coefficient is 5.82. That's the one between air and between the asbestos. And then the outside area here is going to be 2 pi r, this in this case R3, right? R3, and then times L. L being the length of this pipe. R3 we know to be 45 mils, so we just need to multiply by 10 to the minus 3 so that we can have this in meters, right? And then at this point here, I'm going to go ahead and say, oh, for this pipe, because I'm looking for, the heat per unit length, I'm going to go ahead and say for this pipe, I'm going to assume the length of this pipe is 1 meters, right? So if it's 1 meter in length, I need to remember that I did this in the future. So everything I'm going to find is going to be assuming 1 meter length. So this guy here is about approximately 0.608, and that is Kelvin per watts, remembering this caveat. Then the next guy is a conduction one, and this is for the asbestos, so that's going to be the natural log of R3 over R2 divided by 2 pi KL. Again, L we're assuming to be 1, so this is just going to be 45 divided by 30. Note that um, these guys can be in mils because we're going to be dividing the same unit, so it's going to be dimensionless. The natural log doesn't have any units to it. 2 pi K for asbestos is 0.11, and then our L we're assuming to be 1, right? I'm just going to leave it as L so that we remember that we did that. This is about approximately 0.587 Kelvin per watt, again with this caveat there. All right, next one. RC, this is the thermal resistance due to the steel pipe. So this is we don't expect this to be very large, right? Because we know K for the steel pipe is quite high, especially in comparison to the asbestos. So this is just going to be 30 over the 25, and we're dividing the whole thing by 2 pi 46, yeah, 46. And then I'm just leaving L here. L we're assuming to be 1. And this indeed is very small in relationship to everything else. I got 6.3 times 10 to the minus 4. Okay, so about 3 orders of magnitude smaller than everything else with that caveat once again. And then finally, I might put it here so that it's not too far off and we can have all of them on the same page. I have once again another one due to convection, this time the inner one, so I want the inner coefficient and the inner area. Right? So the inner coefficient is the high one, the 1000 581 and 81. And then same thing here, 2 pi, in this case R1 times L. Right? And in this case, RR1, we know it's 25 times 10 to the minus 3 to have it in meters. And this is 0.004. Okay, so about 10 times greater than the one for steel, but still, 2 orders of magnitude smaller than the other two. So pretty much what we find from this is that, these two guys here are where the actual thermal resistance is. The other two are pretty much negligible. So if we didn't have to find the temperatures in between them, so these guys here, we could pretty much ignore them. But we're actually after first trying to find out what is the equivalent resistance. So I'm just going to sum up all these resistances we found. This gave me 1.19965, and I just went ahead and approximated this to 1.2. So this is 1.2 Kelvin per watt, and we're assuming still length of 1 meter. Let's keep reminding ourselves of that. All right, so now we can find out what would be the energy, the heat loss from the inside of the pipe for 1 meter length of pipe. And this is just the difference in temperature. So 80 minus 20, right? The inside minus the outside, divided by this 1.2, which is convenient because this is exactly my 50, right? So it's going to be 50, and that will be watts right there. So this is a Kelvin divided by Kelvin per watt. So it's going to be in watts. But obviously this is for 1 meter in length. So if I double the length of the pipe, I'll be doubling the energy that I'm losing, right? So therefore that will be double. So this is actually, in reality, what we're finding is the amount of energy loss per unit length of the pipe. So that's Q over L, which is 50 watts per meter. So this is, perhaps one of the places you can go wrong in this midterm is forgetting to account for the fact that you assumed it 1 meter. The other option around this is you carry the L with you the whole time, and that way you're going to end up with this, and unit-wise you're going to be more on the safe side because you don't have to remind yourself. You had that from the get-go. Cool. So this is part 1, right? We still need part 2, which is part 2 is looking for T1. So let me go ahead and copy this like we did before. Let me go ahead and copy this. So for part 2, we're looking for T1. And in order to find T1, all I need to do is get. Now that I know the resistances, I can find, there are 2 ways, right? I can do this way or I can do this way here. If I do it the second way, right, if I do it like this, I need to sum up all these 3 guys. If I do it like this, I only need to consider this one resistance RA. So obviously I'm going to choose this one. It makes total sense. I just need to remember that because, we know Q is flowing on this direction here, then I am 100% absolute sure that T1 is greater than 20, so that when I do my delta T, I know that this is actually 20 minus, T1 minus 20, T1 minus 20, because I know T1 is greater than 20. And my delta T has to be equal to Q and times RA in this case, right? So T1 minus 20 equals the 50, and my RA was about 0.608, yeah, 0.608, 0.608. So this means that my delta T is, my T1 is 50.4. And that is because I'm putting this in degrees Celsius. This has to be in degrees Celsius as well. So that is T1. That's the answer for part 2. And we're going to rinse and repeat and do the same thing for T2 and T3, which is our part 3 in this problem. So part 3 in this problem. Okay, so here you go. We can, to find T2, there are 2 ways. Actually, there are 3 ways, right? We can do it like this, like the way that I just did in green, or I can do it like this and account for 2 resistances, or I can go and do like this and account for 2 resistances. I'm going to choose the easy way, only accounting for 1 resistance. Once again, T2 is greater than T1 for sure, so that means T2 minus T1 has to be equal to the Q that we found times RB. Okay, and just like on the previous problem, problem number 1 of this midterm, both our Q and our R are as a function of 1, L equals 1. So if we were to carry the L with us, they would cancel out. So in terms of unit, we're safe. T2 minus T1 that we just found to be 50.4 has to be equal to the 50 watts times RB, which was about 0.587. 0.587. So this tells me that T2 is equal to 79.76 Celsius. Note how close this is to 80, right? Which is the inside temperature of the of the water, right, in the pipe. And remember that I told you when we were calculating the resistance that these two guys here were pretty much negligible. Well, that's exactly what we're seeing right now, right? They're so tiny that the outside temperature of the pipe is very, very close to the inside temperature of the fluid inside the pipe. And once again, to find T3, we have a couple of options. We can go from here, we can go from here, we can do this one, or we can do this one. All of them work, right? I'm going to go ahead and do this one. But like we said before, and this is the conduction the um, for the steel. Actually, there's still, I might do the other one. It doesn't matter, right? It's going to be, the results should be equivalent. The only thing is that this guy is so tiny, okay, that depending how you round it up, both of these guys are small, but this guy is so tiny that depending on how you round up, you're going to get slightly different answers when you solve this. So they're all going to be consistent, but slightly different, maybe the second digit here. Okay, so we'll do this one here. And I know 80 is greater than T3, so therefore 80 minus T3 has to be equal to my Q times RD. So that means that 80, or into T3 will be equal to 80 minus 50 times RD was 0.004. And this gives me T3. T3 is 79.8. So one step closer to the inside temperature of 80, yet still different than my T2. Okay, so these would be the two answers for part 3. So indeed, note how, now that we solved them all, cracked the cases, this is, we found to be 79.8. So we just, 0.2 difference from one to the other one. From this one to this one, this is 79.76, right? So even smaller drop there. And then from here to here, we go to 50.4. So this is, where a lot of the resistance is. And then from here to here, we have 50 to 20. So even a bigger drop, right? So that's what I have for you guys. If you have any questions, as per usual, just leave them down below. If this helped you out, consider liking this video, and we'll talk soon.